Hello everyone, my name is Hussein, and today I will be talking about how to create a GDPR-compliant Iceberg Lakehouse. So I will start by introducing myself. My name is Hussein Awala. I'm a senior data engineer in the ad network team at Voodoo, a committer and a member of the project management committee of Apache Airflow, and contributor to many open source projects, including Iceberg and Voodoo. My journey with Lakehouse technologies started 5 years ago by implementing slowly changing dimensions, type 1 and type 2, using Delta Lake for a financial data platform. Then I had the opportunity to migrate a Parquet data lake of size 2.0 petabyte to a Lakehouse GDPR-compliant using UDI at Leboncoin. And today, I'm working on building GDPR-compliant Lakehouse and analytics platform using Apache Iceberg for Voodoo's ad network. In this presentation, I will start by explaining what GDPR is and the challenges it presents for traditional data lakes. Then I will introduce the Lakehouse paradigm and demonstrate how it can effectively address the GDPR challenges. So GDPR is a regulation in European law designed to protect the privacy and personal data of individuals called data subjects used by organizations called data controllers within the European Union and the European Economic Area. GDPR focuses on 4 main objectives. Transparency by ensuring individuals understand how their data is collected, used, and shared. Control by giving individuals more control over their personal data. Accountability by holding organizations responsible for protecting personal data. And security by implementing measures to safeguard sensitive information. GDPR includes many requirements. Here are the most relevant to data lakes. Data classification by identifying and categorizing personal data. Data minimization by storing only necessary personal data and avoid excessive collection. Data encryption and anonymization by encrypting data in transit and in data store, and using anonymization and pseudonymization techniques when the original value is not needed. Access control by restricting access to personal data using role-based access management and implementing audit access log to edit the access for this data. GDPR underlines protecting data subject rights. This includes the right for data subjects to request access, deletion, corrections, and a machine-readable copy of their data. It also requires defining and automating, if possible, data retention policies to ensure data is retained only as long as necessary. So what are the GDPR challenges in traditional data lakes? First, let's define what we mean by a traditional data lake. So a traditional data lake is a data platform architecture that uses storage services such as object storage or HDFS to store raw data. This data is typically partitioned in tables using IVE style format and stored in columnar format like Apache Parquet. It often relies on IVE-like metastore as a data catalog. Additionally, traditional data lakes use an SQL engine for ETL pipelines. These pipelines transform and aggregate the data, which is then stored in data warehouse for dashboarding, analytics, and machine learning. Data retention policies can be implemented using object storage lifecycles rules, but the retention period will be based on the file creation time instead of the actual event time. In some cases, we have a significant delay between the two times. And for example, in backfill scenarios, in that case, the data will be stored more than it should be, potentially making the data lake not compliant with GDPR. An alternative approach is to use the actual event date as the partition key for the data lake and delete one partition per day using the object storage client. But however, since traditional data lakes doesn't support data file compaction, writing data to random partitions can lead to accumulation of many small files. This results in performance degradation because of the need to read a large number of small files for processing. This also leads to increase the cost of storage due to the more get and list operations on the object stores, and even hitting object storage quotas such as the well-known AWS S3 503 slowdown. Also, traditional data lakes are not well suited for handling export requests because data files in the data lake are written based on the shuffle or the buffer of the ingestion tool. This results in a large number of files to process, which means we have to list and get all the files at least to retrieve the packet footer each time we want to process the requests. And since the data is altered in random order, techniques like data skipping in Apache Parquet don't work well, and we may need to scan most or even all the data. This makes the process slow, expensive, and inefficient even if it's technically possible. So for write to erasure, traditional data lakes typically don't support update or delete operations. To work around this, many companies copy all their data to other data stores that support deletion, like data warehouses or database, then add a 1-month retention policy to the data lake, and only handle erasure requests in a data warehouse or the database because the data in the data lake will be anyway deleted after a month, regardless of whether a request was made. This approach faces the same challenges as the retention policy, which I explained, and it's very expensive due to the high cost of data warehouses. Before we dive into how the Lakehouse paradigm helps overcome these challenges, let's first introduce the Lakehouse architecture and the key features of Apache Iceberg. So, data platforms started with the data warehouse architecture to perform queries and generate insights, but it had many limitations due to the lack of semi-structured and unstructured data, the high cost, and the scalability challenges when the data volume and velocity grow. Then it evolved to a data lake architecture where we store the raw data on no expensive data stores like object stores, and we only move aggregated and cleaned data to the data warehouse for processing. And today, it's evolving into a data lakehouse architecture which combines the flexibility, cost efficiency, and the flexibility of data lake with data management, ACID compliance, and delete and update capabilities from data warehouse with many other optimization features. The data lakehouse has 4 main components: storage, where data files and their metadata are stored. Usually, we use object storage due to its cost effectiveness and scalability. Compute engine, which includes engines that process data using the Lakehouse table format API to interact with the data. Catalog, which enables efficient data discovery within the Lakehouse by keeping track of all tables and their metadata. And lastly, open table format, which sits on top of the data lake, providing an abstraction layer that allows better performance and optimizations to the data. Modern open table formats support common features like the full support of CRUD operations, including update and delete, improved performance and scalability, transactional supports, and ACID compliance, typically through a snapshot system base. Starting from this slide, I will focus on Apache Iceberg, but everything I will explain is similar to other formats as well. So Iceberg has a simple and efficient architecture. The catalog maintains a pointer to the active metadata file. After each commit, Iceberg creates a new version of the metadata file. The metadata file contains table properties, schema, statistics, and information about the different snapshots. In each snapshot, we have a link, a path to the manifest list. In the manifest list, we have information about detailed information about the statistic metrics and the links to the different manifest files. In each manifest file, we have all the metadata of data files, including in that data file path. So Iceberg is a table format rather than a file format. It manages metadata for formats like Apache Parquet, ORC, and Avro, but it doesn't replace them. So Iceberg has 4 main features. Iceberg supports flexible SQL commands to merge new data, update and delete existing rows, and optimize data files. Iceberg also enables seamless schema evaluation, allowing columns to be added, removed, renamed, and reordered without requiring a full rewrite of the data. Iceberg hidden partition feature eliminates the need for extra complicated features to skip processing some of the data files. Iceberg allows querying all the snapshots of the data and drilling back to a previous state of the table as long as those snapshots have not been deleted. Now that we understand what a lakehouse is and the main feature, we are ready to explore how it helps to address the GDPR requirements. Iceberg serves paths and column statistics for data file in manifest files, as I explained before. The upper and lower bounds are particularly important for data skipping, where Iceberg checks if there is an intersection between the filter and the data file bounds, and filter out the files with no intersection from scanning without the need to get the packet file from S3, for example, and read the footer to check if there is an intersection, as we do in the traditional data lakes. And since all data files are indexed already in the manifest file, Iceberg eliminates the need to list the files in object storage, which can reduce the storage cost. And to improve data skipping performance by up to 10 times, Iceberg supports sorting operations as an optimization feature for data files. By sorting data based on columns that are frequently used as filters or aggregation keys, Iceberg can pre-filter more files compared to random file splitting. For example, consider the table from the previous slide. After applying a sorting operations using the user ID field, any equality filter in the new metadata file will lead to scan at most one data file, and all the filters based on the range will be more likely to not find the intersection with one of the 2 data files. So you can check just here. The minimum was 4, the maximum was 800 something, and here we had 12 and 950, and the new data is more optimized because we have sorted data in the data file. This also means that data relevant to the query is grouped within fewer files, which will reduce the shuffle size for any aggregation or join operation. And to optimize analytics workloads with multiple query predicates while ensuring efficient GDPR request handling, we can use Apache Iceberg out-of-the-box the-order clustering technique instead of traditional sorting operation. Additionally, Apache Iceberg supports packet bloom filter, which are very useful in GDPR scenarios. A bloom filter is a data structure that can quickly check if a specific value is likely present in a row group. After Iceberg pre-filter data files using metadata-based data skipping, the bloom filter helps to filter out some of the row group that don't contain the target user ID. I will now show you how we can easily handle erasure requests in the Lakehouse using Iceberg. So in this example, I use Spike SQL to execute comments using Iceberg. So let's say we have an Iceberg catalog called Lakehouse, a database called demo, and 2 tables. The event table used to track user activity on the marketplace website, and the table GDPR request contains user export and delete requests. So handling erasure requests means deleting all the rows from the event tables if there is a user ID in the other table that matches this ID with the type delete. So we check in the GDPR requests all the requests of type delete, then we join with this table to get all the rows we need to delete. So to get this number we need to delete, we can, as I did, filter the request table on type delete and join it with the other table, and we have about 10,000 records to delete. So Iceberg support deleting records with two operations: delete from and merge into. This support makes it easy to manage erasure requests in the Lakehouse. Delete from works with where exists condition, which check if there is at least one match in the other table that meet the conditions. And merge into joins the two tables and apply an action for a set of conditions. The condition in our case is if there is a match, there is when matched, and the action is then delete. So if we find a match for user ID, we apply the action delete. In our case, merge into operation was faster than delete from operation, 5.12 seconds against 6.18 seconds. So, but this is not always the case, where the performance of both operations depends on the size of the both tables and how they are partitioned. So I recommend try both operations and fine-tune the Spark jobs before choosing one. As you know, Apache Parquet is immutable, meaning we cannot update data in the Parquet file. So instead, Iceberg reads the data, load them in the memory, and do the update, and finally create a new version of the data file. So then Iceberg metadata keeps track of different snapshots at the same time to give readers the time, which use the old snapshot, the time to complete the running queries, to allow also incremental consumptions and for time travel queries. This means that our handling for erasure request was not 100% complete, where we can still restore deleted records or query the old snapshot of the data. But fortunately, Iceberg allows. Iceberg supports and recommends regularly expiring or vacuuming snapshots to remove them from the table metadata and also to remove their data, where expired snapshots are no longer available for time travel. So before, I will demonstrate how we can get the snapshot ID from the before the update. So we can use one of the metadata table called history to get and sort it using made current at in descending order, and then take the second row. And in this case, we will get the snapshot ID just before the delete. Then we can use the feature time travel using version as of with the ID we just get. And in that case, we can do that join, and we found that we have the old value. So the data is still there. According to GDPR, we have 1 month to process deletion requests. So if we take the other example, we can use the expire snapshot sort procedure in Spark to expire the data. In this example, I just take all the snapshots, I keep just the last one, but this is not recommended in production because this will lead to fail all the running commands. So instead, I recommend running the processing the GDPR erasure requests every week or 2 weeks, and run a vacuum operation daily that keep 3 to 7 days of data retention for all the snapshots. And to optimize the performance of delete and export query processing, and since both operations are based on user ID, we can use the rewrite data file optimization to improve our files. I strongly recommend using this key to optimize the data after each commit. So we have different strategy in Iceberg. The first one is bin pack, which only compact the file but keep the order random. The second one is sort. For the sort, we can use sort order, like providing different keys. In our case, we need just user ID. But if we have other query to optimize at the same time, we can use the Z order to replace the traditional sort by the order clustering. We can also add a filter if we don't want to optimize the whole table, because our table is incremental. So we can just provide a partition condition, and in that case we will just update and optimize the new data, because the old data is already optimized. We can also provide a lot of other configuration like the target file size, which is the file size we are looking for, and the minimum input files we need to start the optimization operation. And finally, to implement the data retention policy, you can use also the data delete from command with a filter on the actual event timestamp, whether you use the actual time or the ingestion time as partition key, where Iceberg will check if there is at least one record to be retained. So if there is no data to retain in the data file, it will just remove the file from the metadata without any scanning. And if there is at least one record to retain in the file, Iceberg will create a new version, as we saw in the other case. So in both cases, we will have data optimized and with a retention policy like here 60 days without a lot of scanning, and our data lake will be fully compliant with GDPR. And thank you for listening. I'm happy to take your question and here if you have any thought.
Step into the ring with Joe Rice, data's black belt, 2 decades deep, where data stuff is fights are felt, a recovering scientist.